So lesson 6. We're going to change gears a tiny bit. We've been looking so far at point charges, at these circular point charges. What we want to start to do is get our first glimpse into certain things that appear in circuits. And what we want to look at to begin with here, Katie, is parallel plates. Yeah, put the flashcards away. You'll survive. So another important voltage problem is the parallel plates problem. What are parallel plates? Well, they're two pieces of metal, fairly long, or longer, which compared to an electron is huge. And we're going to charge them. We're going to make one positive and one negative. Usually one plate, so large flat metal plates are charged up using a power supply, usually a battery. This is the circuit symbol for battery, a long line and a short line. Usually one plate, labeled positive for higher voltage, is charged to a large positive voltage, and the other plate, labeled negative for lower voltage, is just left grounded. So it either has zero charge, or if this had positive 10 coulombs and this had positive 5 coulombs, you could call this then 5 and 0 or 6 and 1, the difference in charge. If the metal plates, it says, are very large, then, well, first of all, I'd like you to watch. So here's a picture of some parallel plates. You don't need to write this down. One of the reasons we like parallel plates is they have a neat property when it comes to electric field. I'd like you to imagine I have a little positive charge right there. Okay? This plate is positively charged, so it has trillions and trillions of positive charges. This plate is negatively charged. First of all, what direction will this positive charge feel a force, up or down? Think about it. Right. Down, which means which way is the electric field? Which way will a positive want to move it could? Also down. But the electric field has some very, very neat properties between parallel plates. You see, this positive right here is pushing it that way. But there's also a positive right there pushing it that way. The two sideways pushes, Matt, exactly cancel out, and you end up with a net straight line electric field. This would be pushing that way, this would be pushing that way. Again, the two sideways vectors will cancel out, and you end up with, again, a net force straight down. You get a lovely parallel electric field. All the electric fields are in one direction instead of radiating it out in circles. That's kind of handier, easier for us to wrap our brain around, Emily. Is that okay so far? But not only that. Suppose I start this positive right here. It's not very close to the negatives, so there's not a big force from the negative, but it's really close to the positives. There's a huge repulsion force from the positives. Big repel, small attract. What about right here? Well, here now I have a huge attraction force because I'm really close to the negative charges, but I have a smaller repulsion force. What we find is as you move this charge along, the further it gets away from here, the less repulsion there is, but the stronger the attraction is. The further it gets away from the positives, the less the repulsion is. But Nicole, the stronger the attraction is, what you actually find is the force is constant. And remember, I've said to you, well, we can't use this equation because the force isn't constant. We can't use this equation because the force isn't constant. Here's a situation where the force and the electric field are constant. Oh, except, Matt, on the very, very edges, because on the very, very edges, if you're a little charge right here, this is pushing you that way, but there is no canceling charge out pushing you that way. So we're going to ignore the edges, but we're going to say as long as you're anywhere close to the middle, an electric field between parallel plates is constant. It's the same here, 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 which also means the electric force is constant. Connor, that's going to let us do some nice stuff. Not only that, it says this: if the metal plates are very large, then the voltage varies directly with the distance from the plates. Say what? Let's suppose we charge this to 500 volts, and this is 0 volts. Do you know what the voltage is exactly halfway between the two plates? 250. 250. Or let's suppose I charge this to 300 volts and I divide this distance into thirds. If I travel this far, I've gone through 100 volts. If I travel this far, I've gone through 100 volts. If I travel this far, I've gone through 100 volts. And that's why there's a total of 300 volts. The voltage is direct, it's linear. So now you can pick your pencils up. You haven't already. It says this. Let's imagine that we have plates separated by 5 millimeters. Fairly close, a half centimeter apart. And we charge them to positive 500 volts and we leave this one grounded so it's 0 volts. It says, make a graph of voltage versus distance from the lower plate. Okay, starting here and going up, if you're 1 millimeter away, you would be at 100 volts. If you're 2 millimeters away, you would be at 200 volts. If you're 3 millimeters away, you know what your voltage is at 3 millimeters? 300 volts. This is nice because up until now, when we were looking at point charges, Mitsu, as you moved away, it was almost always like r squared or 1 over r. It was math that was tough to do in our heads to keep track of things. This, because it's nice and linear, Katie, we can actually eyeball some pretty easy calculations. Hey, you know what the voltage would be if I've moved a total of 4 millimeters away, Katie? I've gone through 400 volts. And when I get 5 millimeters away, I've traveled through 500 volts. If I were to graph this, it's a nice linear graph. Okay, so it says make a graph, we have. Then it says find the slope. Okay, what's the rise? 500. What's the run? What's the slope? 100. What are the units? What are the units on the y-axis? Volts per. What are the units on the x-axis? Millimeter. Okay. Big deal. Actually, huge deal. Okay. What if we wanted to convert this to volts per meter? Because I don't like millimeters. Let's see. We would go like this. Here's millimeters. Here's meters. How many centimeters in 1 meter? How many millimeters in 1 meter? Yeah, I think 1 meter is 1,000 millimeters. If I wanted to, I can rewrite this slope as 100 times 1,000. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 volts per meter. Big deal, Mr. Dick. Huge deal. Huge deal. I'm not so sure. Yeah. Turns out that right there, volts per meter, it's also the electric field. The electric field between these plates is 100,000 volts per meter, or newtons per coulomb. For parallel plates, there is a constant ratio of voltage drop over distance. If you go halfway, you've gone through half the voltage. If you go 1/3 of the way, you've gone through 1/3 of the voltage. If you go 2/3 of the way, you've gone through 2/3 of the voltage. And here's the key idea. This is what you want to underline or highlight. This ratio is the electric field. That means the electric field is uniform inside the plates, and it's given by voltage difference over plate separation. Say what? Here's your final equation for this unit. Electric field. Now, if I want to find the electric field from a point charge, it was this. Don't write this down. If I want to find the electric field between plates, it's the voltage divided by the distance between the plates. Electric field is a vector, yes, but you know what? Here the direction is going to be from positive to negative. Which way would a positive want to move? It could. In this case, down. Example 2, it says, find the electric field magnitude and direction between the plates. Okay. Symbol for electric field is E. Can I use this equation here? Emily, say no. You know why? There's no radius, and there's not a single point charge radiating it out like an octopus. So even though this is electric field on your formula sheet, nuh-uh. The second equation for electric field on your formula sheet, so not this one here. Change in voltage divided by the distance. Electric field is going to be the change in voltage divided by the distance. If I go from here to here, Brett, what's my change in voltage? Go from here to here, you know, let's call it positive 225. Sure. No, it doesn't, because we're going to decide the direction by using which way would a positive want to move. What's the distance? 3 centimeters. Careful then. What's the distance? Meters. Hello? Meters. 0.03. What's the electric field between these two plates? Mitchell, what'd you get? Sorry? 7,500? Units. Now, I would accept it, Katie, if you said newtons per coulomb, because that's how we measured electric field. But now, as it turns out, another unit that works is volts per meter. Think about it. It's got to be. Direction. All right. Which way would a positive charge right here want to move if it could? Yeah, away from the positive towards the negative, yes? East, if we threw a compass on here, but to the right works just fine. Okay. Example 3, turn the page. It says, how does the electric field at point X compare with the electric field at point Y? It's the same. The electric field is the same everywhere between these plates. It gives us a way to have a constant electric field. Why is it the same, Matt? Well, we said that electric field was the change in voltage divided by the distance. So the electric field at X should be the change in voltage at X divided by the distance at X. And the electric field at Y should be the change in voltage at Y divided by the distance at Y. The Vx on the bottom. not sure what you're asking me. Are you have a concern with this or this? Oh, there's an X there? Yeah, duh. Thank you. Sorry, I just didn't hear what you were asking me. I knew I'd made a typo somewhere. Okay. Okay. What's the total voltage here? 500. What's the total distance here? 5. So how many volts is each centimeter? Do the math in your head. Yeah, 100. See, this is why electric parallel plates are nice. So from here to here, it would be 200 volts, yes, because it's 2 centimeters to location X, divided by, and the distance is 0.02 because it's 2 centimeters. The electric field at location X would be what? 200 divided by 0.02, which is 10,000? No. Is it? It's 10,000 or 1,000? 10,000? Volts per meter. What about, what's the voltage that you go through going from here all the way over to Y? 500, because you've gone through the whole thing. What's the distance that you've gone through? Right? 5 centimeters, 0.05. Is that also 10,000 volts per meter? What about if I went 4 centimeters? What would the electric field be 4 centimeters in? Oh, it would be 400 volts divided by 4. It would also be 10,000 centimeters. The electric field is a uniform between the parallel plates. It says, explain your answer using principles of physics. There. We proved it. In fact, we could probably have done this if we were really clever, Mitchell, algebraically. We could have said, let the distance be x, or 5 minus x, and the volt. We probably could have done a complete algebraic proof to show that at any distance it was the same. They gave me 2 locations. I used numbers. What about here? How does the electric field at point X compare with the electric field at point Y, comparing plates and point charges? Situation A, situation B. Situation A, this is why we like parallel plates. The electric field is uniform, that's the fancy physics word for it, the same, everywhere. It's constant. It only depends on the voltage between the 2 plates and the distance between the 2 plates, but that means it's the same everywhere. Is the electric field right here the same as right here? Well, no, because the electric field for point charges was kq over r squared. Yes? There it is. kq over r squared. So look at location X and look at location Y. Is K the same? Well, yeah, it's 9 times 10 to the 9th for both. Is Q the same? Well, yeah. So Mr. Dueck, maybe the electric field is the same. Is R the same for location X and location Y? In fact, I'm pretty sure the electric field at Y smaller than the electric field at X. Because the further you move away from a point charge, Nicole, the weaker the electric field gets. Okay, Mr. Dueck, I'm buying your argument. Parallel plates, kind of nice. Uniform electric field, easy voltage to calculate. Pretty good. Now, even better, because what we're going to now start to do is say, what if we put a charge in between here? We can do that. We have the technology. In fact, this right here is almost completely the setup to a TV screen. Not the new flat panels, but the older TVs, the ones that when you looked at them from the side, look like that, okay? There was actually a set of parallel plates here, another set of parallel plates right here, and you had an electric gun, electron gun right there. It was very simple technology. I love flat screens, but I'm a little PO'd because 8 years ago when I taught this, all the kids were, that's how my TV and my computer monitor works? Yes. Now it's, that's how your TV and your computer monitor used to work. We're exactly at the cusp of the changing technology. Technical comment, it says, next page. We can see why the electric field is constant inside plates and why it varies with distance from point charge if we graph voltage. For plates, the further you move away, the weaker the voltage, or if we start the voltage here, the closer you move to the positive, the bigger the voltage gets. But for a point charge, it's a reciprocal graph. Those are in Math 12, because R is on the bottom. Okay. So for all electric concepts so far, force, field, and potential energy, I've made a connection to gravity. I said that gravitational force and electrical force equations look almost identical, Joel. I said gravitational field is what tugs on the mass and pulls it to the earth. We said electric field is what tugs on the charge and pulls it towards the other charge, or repels it now, because things can fall up. We said that, charges have potential energy because they want to, I said, fall down or fall up. But I haven't really given you a good gravitational analogy for voltage. Voltage, also called potential, which is the amount of energy per charge, would be analogous to what would be called gravitational potential, would be the amount of potential energy per mass. What's that? Well, if we restrict our engine to close to the Earth and ignore orbit problems, we can use potential energy as mgh. Gravity potential is equal to gh, which is constant times the height. Voltage, Mitchell, is sort of like height. If you have a bigger voltage at that location, it's sort of like you're higher up in the air, and when you fall down, you'll be traveling faster. Matt, sort of. The analogy really breaks down, also because you can fall up, too. Okay? But if you're trying to wrap your brain around what voltage is, kind of think of it as how high you are. Except it doesn't have anything to do with how far away you are. You can have a big voltage that doesn't do with height. Okay. With this analogy, we can think of parallel plate voltage as a steady sloping mountain, and point charge voltage as a curving slope, like a ski hill. The electric field, then, is just the slope of the ski hill. Volts per meter is newtons per coulomb. The field is uniform in parallel plates. Same voltage slope everywhere. Changes around a point charge. In terms of direction, it's which way would a positive want to move if it could. It's actually from a positive voltage to a lower voltage. This means that electric field actually points sort of, if we want to go to our height analogy, downhill. Which kind of sort of makes sense if I wrap my brain around it. Okay. Homework. Take home quiz. Number 1. Number 2. Number 3. Number 4. Take a quick look at number 4. Brianna, what's number 4 asking me to find? Wait a minute. Mr. Dueck, how can I figure out the force? Number 3, if you know the electric field, is there an equation that has electric field and force in it? So now you can start to figure out the force on any charge that's placed between parallel plates. You can start to calculate what force will it undergo. So number 4. Number 5. Mr. Dueck, wait a minute. How can we figure out how much work? Change in energy. Is there an equation that has energy and voltage in? Oh, yeah. Number 6. The field is at the point labeled dot is 100 newtons per kilogram. 7 is good, a little tricky. Oh, that's all good review, but I think I'll leave it. Oh, hey, here we go. Nah, I think we're good. Okay. Shorter lesson. But you got a take-home quiz to work on as well.